Okay, so I think we can start now. Good evening, everyone. Welcome to the seventh live session of this course, Machine Learning and Deep Learning, Fundamental and Applications. So in this particular live session, we'll be basically solving the week 6 quiz. So in week 6, the main topic of thrust was basically the yeah, so ensemble classifiers. So in ensemble classifiers, you might have seen there are predominantly there were three topics. One was the bagging, another one was boosting, and another one was stacking. And for each of the cases, you have seen that what is the algorithm to implement all these techniques, whether it is stacking, bagging, or boosting. So in case of stacking, if I just have to illustrate, 1 second. Yeah. So for let us start from stacking. In case of stacking, what you do is basically you have, let's say, two stage of learning. So in one stage, let's say you have data, let's say your data set is this D, which comprises input features and labels. And let's say this is indexed as xi, comma, yi. And I basically varies from 1 to n. So this is what is your data. So X is basically your feature and Y is basically, let's say this is the problem of classification. So it would be class labels. And in general, class labels in last class also I told that class labels are basically categorical variables. So what you have to do in case of stacking is basically you will be basically feeding the data into separate learners. So it could be SBM, it could be KNN, it could be, let's say, uh, random forest, etc. And these three classifiers will give you individual classification outputs, which could be Y SDM hat, it could be YKNN hat, and it could be YRF hat. So you have got, so you in the input side, so this was your input feature. You fed the input feature into, let's say, n number of different learners. So these are called basically, so these are basically first level learners. And then based on the outputs of the first level learner, you train a second level learners. This is the second level learner. So this could be another classifier. Let's say this in this time, this would be a decision tree. And the decision tree based on the previous outputs from the first level learner, it will try to give you the final classification output. So this will be your final classification output. Let's say y hat. And you basically will you measure the performance, measure the performance between the predicted class level y hat and the original class level, original class level, that is y. So this is what you do. So the main point over here is basically the second level learner learns from the output of first level learner. So this is what stacking basically means. So in general, what you are doing, you are stacking different uh, classifiers at different levels. So this is at level 1 and this is at level 2. So you have stacked in level 1, you have stacked SVM, KNN, RF, and in level 2, as because you will be doing a global classification based on these local predictions, this is the second level of second stack of classifier. So over here you have used decision tree only. So this is what stacking basically means. So why I am discussing this? Because majority of the questions are based on the concepts which I will discuss shortly, because I am not going to discuss the whole concept of stacking, bagging, boosting, etc. So majorly I will be explaining the gist of the these topics. So this is what stacking means in a very naive way. So now let us see uh, what is basically bagging means. In case of bagging, what you do, let's say again, let us consider you have a data set D, which is having xi, comma yi. And again, the problem is, let's say, classification problem. So majorly we will talk about classification problem. And in general, if you see any of the courses of deep learning, machine learning, the major concern basically lies in the classification problem. However, you can, based on your application, you can talk about classification, regression, segmentation, etc., etc. Because there are several problems that you can handle with using machine learning, deep learning techniques. Okay, fine. So in case of bagging, what you do, again, you let's say take X as the input to the model and you form different classifiers. Let's say it could be SVM. Let's say it is a linear SVM. So in the last lecture, we had seen that what is a linear SVM in the Python implementation section. Then let's say you have taken another SVM. Let's say this is a SVM. This is a quadratic kernel SVM. Let's say you have another SVM that is SVM cubic kernel. So all these things we have seen in the last class. Then let's say you have random forest. Then let's say you have KNN with k equal to 3, k equal to 4. Like that, you can increase the number of uh, classifiers, parallel classifiers. Fine. Now, in case of bagging, there is a catch. Initially, in stacking, we used the whole data to train these parallel models. But in case of bagging, what we do, instead of passing xi, all the xi directly, what we do, we feed x tilde, and x tilde is randomly sampled from D x comma y with index I with so what sort of sampling do we use here? Can any one of you tell me? In case of bagging, what sort of sampling do we use?
Random sampling with replacement.
Yeah. So we use random sampling with replacement. And based on this, we get a new set that is, let's say, x tilde. So we can do it n number of times. And let me write it. And we can do this sampling n number of times if we have n such classifiers. So if you have n number of classifiers, you have to sample x hat n times from the original data set. And then what it will do, it will give you individual outputs. Each of these classifiers will give you individual outputs, which I can write it as y1 hat, y2 hat, y3 hat, y4 hat, y5 hat. And then what you do, you take all the predictions and you do a thing that is called majority voting. So this majority voting is something like that. Let's say you have two class classification problem. Let's say you have some mammogram images, and based on the mammogram images, you have to tell whether there is any lump has been formed or not. So that means whether the mammogram image represents cancerous lump or non-cancerous lump. So output could be, so original Y could be either, let's say, cancer or let's say healthy. So what they will do, they will also generate the categorical variables. Let's say in this case, this is cancer. In this case, this is healthy, this is healthy, this is healthy, and this is, let's say, cancer. And let's say, in general, we have, let's say, in number of such predictions. But in our case, let's say we have only 5 such classifiers. So we have 5 such outputs. So in case of majority voting, what we actually do is basically we try to generate the mode. So mode is basically whichever entity is repeated is coming frequently. So we calculate that one. So in case of mode, what we write mode of y1 hat, y2 hat, y3 hat, y4 hat, y5 hat, and dot dot. So in our case, if I just evaluate this C, H, 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 C, dot dot, and from here we can see that H is occurring more frequently than Cancer. So therefore, the mode for H is high, and over here mode of H is equals to 3. So for whichever class the mode is highest, so over here we can see the mode of C is equals to 2, mode of H is equals to 3. For whichever class this mode is highest, we consider that the given input basically belongs to that particular class. So over here we can say that X hat belongs to class C. So cancerous class. Sorry, so this would be class H, healthy class, as because for healthy class the mode is highest among healthy and cancer, and therefore X hat belongs to the healthy class. So the main fundamental thing is basically you have n such classifiers working parallelly, then decision is taken based on the majority voting. So what we are doing, so over here we are making the decision. So this is the decision making process. So how we are making the decision? We are making the decision based on majority voting. So decision is taken based on majority voting of the outputs received from n number of classifiers. And the third point is, as because we cannot feed X directly, so we create X tilde, which is a subset of X. And this subset of X that we have created, so that is by, so by random sampling with replacement. These are the 3 key points that you have to remember whenever you see any sort of problem related to bagging. And another point, what bagging basically do is, so over here you can see that you can use n number of such classifiers. And based on n number of such classifiers, you are getting n number of such outputs, and then you are doing majority voting to get a single output. So over here you will get a y. Rather, I can write it as y hat. So if you rely on a single classifier, let's say you are relying on this single classifier, then what would happen is, let's say you are using knn with k equal to 1 or 2, or let's say knn with k equal to 1. So we know that knn with k equal to 1 is extremely susceptible to overfitting. So in kn's lecture, we in the week 4 quiz, there was a question that if you have knn with k equal to 1, it basically suffers from, there were several options. The true option was overfitting. So the point is, if you rely on a single such classifiers, in some of the cases, you might see that there is a problem of overfitting, because some of the models will be very specialized for classification. So what it will do in the training time, it will reduce the loss or reduce the error significantly. However, at the time of validation or testing, it will not be able to perform well, because what it has basically seen in the training time, the training data set, it has just marked up completely. So it has remembered everything. So therefore, in the training phase, it is giving you perfect result. However, at the testing time, you will see that your model is failing to classify. So there is a problem of overfitting that you can see. So I can write that uh, relying on single classifier may lead to overfitting. However, bagging helps to mitigate this issue. So what we are doing in case of bagging, we are relying on a number of classifiers, and not only that, we are using majority voting. So which might help us in doing the classification in a better fashion. So bagging helps to mitigate this issue by considering majority voting. These are some of the key points that you can just refer to. So this is a naive view of bagging. And now if I just talk about boosting, so in case of boosting, what you do, let's say you have D data set X, Y, which are indexed with I, and let's say you have n number of such samples, so Xi and Yi. So you feed Xi, or let's say total X. So over here, you do not have to do any sort of uh, random sampling with replacement. So you can feed X. So you can feed X to a model, and then you will get output Y hat. So some of the Y, let's say some of the Y will be misclassified. So I can write Y misclass belongs to Y hat so out of, so I can write it in this way as well. So Y hat is basically union of Y hat misclassify comma Y hat correct classify. So that means when you predict Y hat from X using a trained model, you might incur some misclassification as well as some correct classification. Now, what is your job in case of boosting? So from the name itself, you can get an idea that you want some sort of a boosting. Now, for which you want to get boosted up to increase the level of accuracy while doing the prediction. So if your model is doing, let's say, it is giving you suboptimal performance, let's say 60% or 70% accuracy you are getting from a trained model. So what you want is you want some way to boost the model's performance such that your classification accuracy will go and misclassification rate will go down. So that is why the algorithm is basically called boosting. So in case of boosting, what you have to do, based on, you have to first identify which samples you have done misclassification for. So the first point is find the misclassification or misclassified samples. And then put some sort of weighting factor to upweight the misclassified samples and downweight the correctly classified samples. And again, train the model. And if you find error, again follow step 2. So this is your step 2. So what you have to do, you do classification based on the first you take the data, you do the classification, you find some misclassified samples, then you have to create some sort of a weighting factor so that the misclassified samples will be some sort of, they will be put more attention to. So you have to pay more attention for the misclassified samples such that you do not do any sort of misclassification in the next stage of iteration. So that means you have to put more attention to those particular samples on which you have done misclassification such that in the next stage they are not uh, misclassified again. And as because in the first stage you have done correct classification for some of the samples which are correctly predicted, so there you can downgrade those samples because anyway you have done correct classification. So there is nothing to put more attention for those particular samples. So after doing this, you retrain the model. So this model you will basically carry forward, and from this particular X, what you do some sort of a weighting. The data set will be weighted, either up weighted or down weighted, and again the model will be trained, and then again it will give you some prediction. And then this particular loop will go on based on how many times you want to do this operation. So again, it will be weighted, and then again model will be trained, and then again it will give you the prediction. So y hat, so y hat 1, y hat 2, y hat 3, like this. And then what you can do, you can again take some sort of an average or majority voting. So over here also you can take majority voting, otherwise you can take average representations to get the final classified output. So effectively, rather than using different models at different time, so we are reusing this particular model based on this weighted data. So in the previous case, we were just sampling the data. We had fed the data into n number of parallel models, and we got some output, and then we took majority voting. We were not at all bothered about improving individual models again and again. So there, the main concern was, I will train n such parallel models. Whatever classification result will come, I will just check mode, or I will check that whichever class is occurring more frequently, that will be the correct classification or final classification. Over here, the main point is, initially we started with this model. We saw in the output there are some misclassification. Now we'll be here the main part is, over here we'll majorly focus on weighting the data in such a way that misclassified samples will be highlighted more. And if the misclassified samples are highlighted more, then the model will try to do correct classification, or it will try to understand some data representation from those misclassified samples, and how we will put more attention to those samples by weighting the actual data set. And then based on the weighted data, we will retrain this model. So what we are doing, we are reusing this particular model. Again, in the next stage, if I see in y hat 2 dash, if I see that over here also I'm doing some sort of misclassification, I will again weight the original data set, and then I will reuse the model, retrain it again, and I will get the classification result. So you can actually do this in number of times. So you have to, if you want to do it a number of times, you have to change the iteration from, let's say, 3 to you can put 50, 60, something like that, based on your application. And then again, we'll combine all these results, and then we can do majority voting or averaging, and then we can get the final output, that is y hat. Okay. So over here, you can see that this is the implementational algorithm. And there are certain equations that you'll see already. You have seen actually in the week's lecture, that how we can calculate the error, how we can calculate the weighting factor. So every time when I'm basically talking about weighting, so you have to numerically define that how you can weight. So therefore, you have some sort of a variable that you have to introduce, by which you can weight the data set or weight those particular samples. And for that, there is a term that is called alpha. So this is basically the weighting factor. And over here, majority voting, average, all those things are there. But specifically, in majority of the cases, you will see the output, that is basically we can get from the combined combined individual outputs, that is called weighted linear combination of all the individual outputs. So this is actually what we do in practice. Averaging, averaging is also some sort of a linear combination. You put a uniform scaling factor for all the outputs, but rather in practice, in the algorithm, in the AdaBoost algorithm, that is very uh, popular in case of boosting methodology. So over there, we use weighted linear combination of all the individual inputs, all the individual outputs. And then we can get the final output, that is y hat. And there are several functions that you can see. For example, what I was talking about. So this alpha, the weighting factor is basically based on the error that you receive. So it is measured as half ln 1 minus e by e. So e is basically the error rate for a misclassified sample. So there are certain numerical problems that you will see in the week's lecture. So let us now move to the quiz part. Okay. So in the first question, in AdaBoost, the final prediction is determined by. So uh, already we have talked about, so that is why I told initially as well that the discussion that I am doing for each of the cases will basically help you in finding the answers of this particular quiz. So that is why I was putting much time over here in discussing all these concepts. So this is the in general boosting structure. So in general, if I'm not be very specific about any particular algorithm, so there we generally use either we use majority voting or averaging. But as because there is a very popular technique that is called ADA boost. So in ADA boost, in this particular case, instead of using majority voting or averaging, what we use is basically weighted linear combination of the individual outputs. So that is what we do in case of ADA boost. So now let us see that what was the options that have been given to this question. So in ADA boost, the final prediction is determined by a simple average of weak learners prediction. So we do not do simple average. Already I have told that in general, if it is called boosting, then we say average voting, a majority voting, averaging, etc., etc. But this is specifically, they have mentioned that ADA boost. So we have to follow the main algorithm of ADA. Then, so this is incorrect. The prediction of last week. So this is also incorrect because as per the diagram of mine, we do not use Y3 only, Y3 hat only. We use all the predictions from each of the weak learner states. For example, Y1 hat, Y2 hat, Y3 hat, etc. So the third one is weighted sum of weeks learner prediction. So this is what we do. So that is weighted sum means this is also called linear combination. So this is this somewhat looks like this. So W1 into H1, W2 into H2 dot. So here H1, H2, these basically refers to the prediction from weak learners. So a weighted sum of weak learners prediction. This is the correct option. And the last one is a random selection of weak learners prediction. So this particular line basically tells you that your y hat is a random selection. It could be, it belongs to either of, if I just mathematically write it, it is either y1 hat or y2 hat or y3 hat. So this is what this particular statement means, that y hat, the final prediction, belongs to either y11 or y22 or y3. However, this is also incorrect because we do not do this sort of operation in case of ADA boost. So thereby this is the correct answer. Then boosting algorithm assign equal weights to all training instances. So equal weights to all training instances. So in case of boosting, already we have seen that how we basically assign weights for each of the cases. So there we do up weighting and we do down weighting. And specifically up weighting we do for misclassified samples, and down weighting we do for correctly classified samples. Right? Now, if I just further make some other discussion on up weighting. So let's say your initial weight was W naught. So for misclassified, so for misclassified samples, WT was, let's say, initial weight. WT plus 1 is basically WT into exponential of alpha t. This is for the misclassified sample. So this is where you are doing up weighting. And for correctly classified samples, WT plus 1 is basically WT into exponential of minus alpha t. So you can understand that if you put exponential of minus alpha t, the value will be quite less, because if you put exponential of minus something, the value will go down. So therefore, this is basically the down weighting. And we'll see a numerical based on this particular formula as well in the next class, where alpha t is half ln 1 minus epsilon t divided by epsilon t. and epsilon t is the misclassification error rate. Fine. So boosting algorithm assign equal weights to all training instances, which is incorrect. It does not weight equally all training instances because already we have seen that it either upweights or downweights based on whether your samples are misclassified or correctly classified. Weights inversely proportional to the class distribution. Again, this is incorrect because we do not do weighting based on class distribution. There is nothing related with class distribution as far as weighting is concerned. Fourth one basically tells you random weights to each base model. Again, this is incorrect because we do not do random weighting. We are using some sort of deterministic method to weight the model. So over here, the deterministic method is we are multiplying the previous weight with the exponential of the weighting factor, and we are down weighting with exponential of minus of the weighting factor. So therefore, randomly weighting is also an incorrect option. So let us see what is option 2 is saying. So in option 2, we can see that this is saying that weights based on the difficulty of instance. So obviously, based on the difficulty means, for example, whether it is difficult to classify, that means it is misclassified. These samples are difficult to classify. If you incur that some of the samples are misclassified, that means obviously this is somewhat difficult for the model to get it correctly classified. So over there, to reduce the difficulty, what we are trying to show that we are trying to tell to the model is basically look at those particular samples which we have upweighted through some sort of numerical manipulation. We have upweighted these samples. Now the model can look at very clearly, and now you can do the classification pretty well. So that is what we are doing. So based on the difficulty, whether it is classifiable or it is misclassified, we are doing the weighting process. So therefore, weighting based on difficulty of each instance is the correct answer. Fine. Okay. Consider a binary classification problem where a single weak classifier has 60% accuracy. So the problem is binary classification problem. So that means y could be either +1 or -1 class. So when a single weak classifier is basically employed, then the accuracy is 60%. So accuracy is equal to 60% when only single model is used. By combining multiple classifiers through majority voting, the classification accuracy improves. If uh, if five independent classifiers are combined, what is the probability that ensemble accuracy will exceed 60%? So now five classifiers have been employed. We have to find the probability that accuracy is greater than equal to 60% for, or let's say I can write while using 5 classifiers. So this is what we have to uh, evaluate. So can any one of you tell me that what sort of ensemble learning technique is this one they are referring to in this question? Yes, anyone? So you have read the question. So can you identify that what sort of ensemble learning that we are doing? So we have seen 3 different techniques. So what technique is this one? Okay, so this particular technique is basically refers to the bagging process. So you can see that we are using 5 independent classifiers. So that means given the data X, you are using 5 independent classifiers. And then what you are doing? You are doing majority voting. So you are combining the results of all these classifiers to majority voting. So this process is basically, so these were the learners, different learners, and then the output is merged based on the majority voting. So this is what is uh, bagging looks like. So this is the process of bagging. So let's say you are using 5 different classifiers. So the question is, if I just frame another question, let's say uh, you are using 5 classifiers, then for what condition you can say that accuracy of majority voting is 60%. So first they are asking in the original question, they are asking accuracy greater than 60% while using 5 classifiers with majority voting MV. So I am asking the question, let's say you are using 5 classifiers, then for what condition you can say that the accuracy of majority voting will be equal to 60%. At what condition you will say you can say this? So let me give you an example. Let's say you have X and the corresponding label is, let's say, spam. So you are doing email classification, whether this is a spam email or non-spam email. So you have trained 5 different models, SBM, KNN, RNN, etc., etc. And let's say your Y hat. So this is your original Y, which is supposed to be spam. And you are predicting from 5 different models, that is non-spam, spam, 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 non-spam. So your sample space is 5. So total number of NS is equals to 5. Now, if you do majority voting, what would be the output after majority voting? That is spam, because you can see that spam is frequently occurring than non-spam. So therefore, output is spam. And you can see your original. So this is your Y hat final. So this is your, or this is Y hat I based on all the models. So this is your original level, and this is your final prediction, which is also spam. So that means you are doing correct classification. And for doing the final correct classification after majority voting, how many individual models have to give you spam? At least 3 models have to give you spam, such that, so over here, if you just evaluate the probability, your total sample space is 5, and the number of correctly classified samples for each of the individual model is 3. If you just take the percentage format, so it's 20. So I can write this is a 60%. So that means to get 60% probability of correctly classification using majority voting, at least 3 of such individual models, 3 of such 5 individual classifier should give you spam, spam, spam. So which is basically, one second, which is basically the 60% condition. Now in this particular question, they have given that they're asking greater than 60%. So that means what are the conditions? So the conditions are probability x equals to 3 plus probability x equals to 4 plus probability x equals to 5. So then only you can get 60% and above classification accuracy. This is why I was asking this question, that at what condition you can say that you can get 60% accuracy. So this is the condition. So that means at least you have to ensure that 3 of the individual model will give you the same output as the original one. And as then you can get 60%. And if you have to achieve accuracy greater than equal to 65, that means you have to consider at probability x equal to 3, x equal to 4, and x equal to 5. Okay. So probability 60% or above after MB is equals to probability at x equal to 3, probability of x equal to 4, probability x equal to 5. Now, how you can evaluate these probabilities? So already the question states that this is a binary classification problem. So this is a binary classification problem. So if this is a binary classification problem, your output would be either +1 class or -1 class. So this is a discrete sort of data, discrete sort of classification data that you can consider. And there are only two options, either yes or no. So you can consider that this is either yes or it is either no. So this is a discrete case. This is a discrete case. In the last class also, I have given a example that how the classification problem is basically a discrete case of prediction. So from that point of view, I can say that this follows Bernoulli distribution. In case of Bernoulli distribution, what is the probability density, probability mass function? If you have 10 such trials, and if you have obtained, let's say, k for k such cases, you have obtained either it is success or it is failure, then it would be NCK probability of k and 1 minus probability of k. Fine. So over here, the probability that they're asking is basically for 6. It is 60%. So 1 minus p is your 40%. And this k is basically either 3 or 4 or 5. And your total number of sample space already we have talked about in the last slide. So total number of sample space is basically 5. So we have to use these informations and then we can get the final answer. So if I just evaluate this, I can write 5C3 and then 0.6 to the power 3, 0.4 to the power 2. Oh, sorry, it would be 1 minus k. And then it would be 5C4, then 0.6 to the power 4, 0.4 to the power 2. Sorry, it would be 1. And then over there you have 5C5, and then you can write 0.6 to the power 5 and 0.4 to the power 0. So if you so this is just like 5 factorial, 3 factorial, 2 factorial, and then this thing. Then over here, this is 5, 4, 1, then this thing, then this 5, 5, 0, and then this thing. And this will effectively give you the final result as I have already pre-computed this 3456 0.2592 plus 0.07776. So if you sum up all this, you will get 0.6822 n. So therefore, 68.26 is basically the correct answer. So the main crux of the problem is you are using 5 such classifiers. So you have to see that at what condition you will get 60% accuracy. So to get 60% accuracy, at least 3 of the model should give you the correct classification. And now the question says that 60% and above. Exceed means it basically it is greater than equal to 60% condition that it is referring to. So if you if your three models, if three of your model basically gives you correct classification, that means it is 60% case, and rest of the case basically refers to greater than 60% case. So if you add three cases, you will get the correct answer. And what is and how you can basically calculate these cases? So it is basically from the Bernoulli's distribution. Fine. Next is dash is useful for high variance models. So already in the discussion, if I just go to the discussion part. So for bagging, we have already showed that uh, if you rely on a if you rely on a single classifier, you may lead to overfitting condition. And bagging basically based on all it basically tries to see all the prediction results, and based on the prediction it takes majority voting to get the final classification accuracy or final classification output. So therefore bagging basically tries to help uh, avoiding the overfitting condition, as because it tries to mitigate the issue by considering majority voting from each of the parallel or individual classifiers. So therefore, straight away you can, one second. So straight away you can tell that uh, bagging basically is useful for high variance models. So high variance also refers to overfitting. So why it is high variance? If I just give you a short uh, reason. So let's say this is your loss, and this one is basically the model complexity. So this is your training loss. And let's say the blue one is your testing loss. So variance means the spread between two data. So you can see that this particular data and this particular data is there is a very big gap. So this gap basically refers that there is a high variation or high variance between the training loss and the testing loss from this point or from this point onwards. So there's a funnel like shape. So this refers high variance state, and this also named as overfitting issue. So therefore, bagging basically tries to mitigate overfitting or high variance issue. Okay. Now, next question states that bagging technique combine the predictions of the base models by taking average of the prediction, taking maximum majority vote, weighting the predictions based on their performance, ignoring the presence of predictions of base model. So obviously, ignoring the prediction of base model, it is incorrect because it uses n number of parallel such models, and then it generates n number of parallel model generates n number of parallel outputs, which is basically then used in conjunction with majority voting to get the final output. So weighting of prediction based on their performance, again, this is incorrect because weighting we do not do in case of bagging. Weighting we do in case of boosting. So this is for boosting. Then taking average of their predictions. So over here, we do not do average of the prediction. Rather, what we do, we take the maximum or majority vote. So already we have already discussed in the discussion as well. Okay. So here is a small correction. So in the second iteration of ADA boost, the weight assigned to a misclassified data is 0.4. So W2 is 0.4. If the initial weight for all data point is 1, so W1 is 1. What is the misclassification rate? So misclassification rate is basically epsilon of the data point at the end of second iteration. So has anyone tried this? So they have given the weights at first iteration, at second iteration. So now the question is how you can evaluate epsilon or the misclassification error rate. WT plus 1 is WT multiplied with ln, multiplied with e power alpha. And this is for misclassified sample. So they have said that this is misclassified data point. So for misclassified data point, we do e to the power alpha. For correctly classified samples, we do e to the power minus alpha, because e to the power minus alpha, what it will do, it will create a small weighting factor, and therefore you will do down weighting rather than doing up weighting, because e to the power alpha is monotonically increasing in nature. So therefore, this is the equation that you have referred to. Additionally, alpha is half ln 1 minus epsilon divided by epsilon divided by epsilon. Therefore, I can write I can plug this particular formula inside this. So Wt plus 1, Wt epsilon, exponential of half ln 1 minus this divided by this. So I can write it as Wt e to the power ln 1 minus epsilon by epsilon to the power half. And even I can write Wt 1 minus epsilon half ln e, and ln e we know that it is 1, so I can just omit this. So this is what we can analytically, we have got a closed form solution. Thereby, if I just plug in all the values, so this is 0.4 is equals to 1 minus epsilon divided epsilon to the power half. So it would be 0.16 1 minus epsilon. And if I just cross multiply, so this would be 1.16 epsilon equal to 1. So epsilon will be 1 divided by 1.16. So it would be 0.86. One divided by 1.16. So 0.8620. So if I take percentage of epsilon, so it would be 86.20%. So therefore, this is the correct answer. So this is a pure formula based question that they have asked. So they have given a misclassified sample. So for misclassified sample, the equation is this one. They have given all the values. So there is another function alpha is there, and the function of alpha is represented using the error rate formula. So I can get a closed form solution from this to this, and then I can plug in all the values so that I can get the final result. Fine. Okay. So the seventh question states that which of the following does bagging help to reduce the machine learning knowledge? And again, the important thing over here is, so the besides the question, that you can see that in majority of the cases, you will see this round shaped bubbles. So this round shaped bubble means there is only single option. It's a uh, single option correct type question. Rather, if you see there is a square type of box, is a box is there, then uh, first thing you should basically consider is there could be multiple options which can be correct. So this is an indication that in your final exam also, if you write the final exam, so there also you have to keep in mind that if you see any sort of square boxes beside the options, so there might exist some cases where multiple options may be correct. So you have to be cautious about that. So in the seventh question, this states that what basically bagging helps to reduce in machine learning model. So already we have seen the answer that I just referred to this particular slide. So bagging helps in reducing overfitting, and the analogous term of overfitting is high variance. So bagging helps to reduce overfitting, and overfitting is analogous to high variance. So this is the main point. So from this, let us now scan the uh, options. So it reduces obviously variance, models variance, and it also reduces overfitting. Bias, let me just give you the answer. It does not reduce bias, rather boosting technique helps in reducing the model's bias. Bagging does not help in reducing bias. Boosting does helps in reducing bias. That you can also add in the key points on boosting technique. And so as the model complexity is being considered, model complexity, in case of bagging, you are parallelly training n number of individual models. So bagging cannot help in deciding that what would be the complexity of a decision tree if you are using, or a random forest you are using, or whether you should use SBM with cubic kernel or linear kernel. It has not no it has no say on this. It basically tries to exploit all the individual outputs it basically gets from each of the individual or parallel models. And based on their prediction, it tries to use majority voting to get the final prediction out. So therefore, model's complexity in each of the parallel model has no relation with bagging, because bagging does the majority voting of the outputs that has been received from each of such parallel models. So therefore, model complexity is not the correct option, so as the bias option. This is also not correct. Okay, so random forest can handle. So this question we have seen in the question was on decision tree. The same question was on decision tree. So if you basically merge large number of decision tree, that effectively becomes the random forest eventually, because you have lots of tree, and which basically gives you an ensemble amount of data output or class output, or it could be a regression output as well. And then you combine all those to get a random forest. So whatever property that holds true in case of decision tree, that will also be applicable for random forest. So from decision trees lecture series, we have seen that decision tree can very well it can very well deal with any sort of data set, whether it is a small data set, large data set, it doesn't matter. It tries to heuristically uh, find the Gini index or the entropy based measure to maximize the information gain. And then based on information gain, it tries to formulate the features distribution such that it can do the classification. So therefore, large data set is not a constraint for random forest. So it can handle large data set. Again, it can handle any sort of data, linear, non-linear. It does not matter whether it is a linear data, non-linear data. It doesn't matter. And random forest, we have seen in decision tree lecture as well, that using decision tree in the last lecture, there we had done some sort of linear regression problem. And in the week's lecture by Professor MKB, so Professor Bhuyan had shown a problem of classification. So there were 3 columns, 3 to 4 columns, let's say outlook, whether the temperature is high or not, whether it is cloudy or not. Based on that, you will take a decision that whether you want to play tennis or you skip going for tennis. So that was a problem of classification. Based on some input attribute, you want to take decision that whether you'll go for tennis or not. So therefore, that was a classification problem, and we did a similar problem for regression in the week's quiz. So there is an indication that the decision tree can handle both classification and regression problem, and thereby uh, random forest will also be able to handle classification and regression task very easily. Because the main fundamental point is basically, if whatever point basically holds true in case of decision tree, that will also be holded true for the random forest case. So therefore, all 3 cases, this handling larger data set, linear, non-linear data, and classification and regression tasks, all are true. So therefore, all of the above is the correct answer. Okay. So in this particular question, it is basically asked that in stacking, what is a meta learner? So if I draw stacking, so what there you have X, you have some data, parallel data going to different models. Let's say model 1, model 2, model 3, and model 4. So these model will give you some prediction, y hat 1, y hat 2, y hat n. Now, in case of stacking, you do not do majority voting. What you basically do, so these are called first level learners. So based on these outputs, you train another model. Let's say M tilde, which is called second level learner, or in this case, it has also named as meta learner. Why it is called meta learner? Because it is learning not from the input data. It is learning from a meta information or an intermediate information, which is basically yielded by these individual models. So this is called first level learners, or I can also call it as base models, which has basically run in parallel. And then these y hat, y2 hat, dot 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 yn hat. These are called intermediate outputs from each of the base models, and which is subsequently fed to the meta learner. Meta learner learns from these outputs, and then it gives the final prediction y hat final. So therefore, we can see that meta learner learns from the previous outputs yielded from the base models. So this is the observation that we can do, that this meta learner M tilde basically learns from the previous outputs, which is basically generated from each of these individual parallel models. And then it tries to learn from these data to get the final prediction. So from this particular logic, now let us try to scan the solution. So in the first solution, it is stated that a model that performs data pre-processing, which is incorrect. While training a particular model, so these are the initial models. While training this model, you use the data. So your data set is xi, yi, index I. So this is your feature or input feature. So this is where the main data lies, and this is the class labels. And this is the class labels. So in xi hat, you basically do pre-processing. So what could be a pre-processing technique? This could be normalization. Then this could be, let's say, outlier removal. We already know what is outlier. So pre-processing you basically do on X, not these Y hats, Y1 hat, Y2 hat. You do not do pre-processing on these things. And so as the M tilde also do not, it also does not perform pre-processing on these data. It has some other purpose. Pre-processing, a model that performs data pre-processing, it is totally incorrect. Then a base model trained on original data set. So it is meta learner. So meta learner is basically the second level learner. However, the first level learners are called the base models. So anyway, a second level learner cannot be a base model. So therefore, what is the meta learner? It is a base model trained on original data set. Then the third option states that a model trained on the prediction of base models. Yes, this is true because it is a model. It is a second level learner or a meta learner. It is a model which is trained on the predictions of the base model. So these are the base models. These models predicts y1 hat, y2 hat, dot 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 dot, all these things, which is subsequently fed to the M tilde, and M tilde tries to learn from each of these data points to generate the final output. Therefore, a model trained on predictions of base models is the correct one. And let us see the final option. So the final option states that a model used to aggregate the predictions of base model. So we are learning from the predictions from the base model. We are not doing aggregation. Aggregation means basically the average. So this particular line states that y hat is 1 upon n, y1 hat, y2 hat, dot, 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 yn. Are we doing this? We are not doing this. What we are doing, we are putting another model which tries to learn from these data to get the final prediction. It is not at all an average process or an aggregation process. So therefore, this also is not the correct option. So it is a model trained on the predictions of base models. So this is what it basically means. So with this, we have solved the week 6 quiz, and I will basically upload the PDF of the solution in my G drive, so which you can access from the link. So I can do that right now itself. So you will find that in each of the for each of the weeks session, I have uploaded both the unannotated version and annotated versions. So you can just download the unannotated version and then you can solve on the sheet itself. So if you have any question, you can ask. Otherwise, we can stop the session.
Sir, where I can get the drive link?
Uh, uh, can you see my screen? I think screen is shared still. So let me just show you. Uh, So when you go to the course website, there you will see the live session. Oh, sorry, there you will see this problem solving session. In the problem solving session, go to recording. And then it will take you to a Google Sheet. And from here you can access. The drive link is pasted here, presentation folder link. So from here, you can access all the week's content that have been uploaded till now.
Okay, sir. Thank you.
Okay.
And sir, in the final exam, only MCQ will be there, na?
Yeah, it would be MCQ. Majorly some, if you have seen the last week's live session of Professor M.K. Bhuyan, so here he mentioned that the final exams question might be somewhat more easier than the week's quiz. So majorly some reasoning based question will be there, and you'll find very few numerical questions, but all of them will be MCQ only.
Okay. And the date is fixed, 3rd November.
Yeah, the date is fixed. I do not exactly know the exact date, but from the very beginning of the course, they basically declared the date of the examination, so that is fixed.
As in, it's in Diwali vacation. That's why I'm asking.
Uh,
Question.
yeah, in the last class also, someone just asked me to tell this thing to the NPTEL team. I mailed them, but for question for the exam, I don't think so. They will consider unless and until you guys can put this particular query in the Q&A forum as well. So they might then look into the problem.
Okay, sir. Thank you.
Okay, so I think now we can stop the session here. So let me just stop sharing.
Mm.